Great. Great. Well, yeah, thanks a lot for the invitation to visit Amsterdam and to speak today. I've spoken to you once before on Zoom, and that was already a lot of fun. So I'm sure being here in person is still more fun. Okay, so what I want to talk about today is at the interface of quantum information theory and quantum gravity. And the interplay of those two fields has a very long history, going all the way back to the birth of quantum information theory, around the time of the birth of quantum information theory, John Wheeler's group in Texas, and yeah, many other interactions between the fields since then. But what I want to talk about today is about pushing that connection into a new sort of mode. So I think historically these fields have interacted sort of in the form of either quantum gravity inspiring interesting questions for quantum information theorists, or tools from quantum information theory being applied to quantum gravity. But what I've been aiming to do, and what this is starting to get closer to, is a different mode where really quantum gravity, just in a very direct implication sort of way, tells us something new about quantum information. I don't, in some limited ways, we were able to achieve that, but there's a lot more to do, and I think this is an interesting connection to keep thinking about. Okay, it's not working. Good. Okay, so within quantum information theory, the subject that I want to think about is the question of understanding information processing when you're subject to causal constraints. Okay. So the way that I'm going to summarize the set of causal constraints that I'm interested in is with a picture like this, which I'm calling a causal network. So in the causal network, we have some set of input, or it's a directed graph. It has some set of input vertices, which I'm always going to draw at the bottom, some set of output vertices that are going to be at the top, and then some set of causal connections between them, and possibly some intermediate vertices sort of in between. What this represents is that at, say, this vertex, there's going to be some input quantum system A, at this vertex, some input quantum system B, and then at the vertices, we can do local operations on whatever quantum systems are present there. And then along the directed edges, those represent where we can send information or how we can communicate. And then again, at these later vertices, we could again do some local quantum operations. Then generally, the kind of question that we want to understand is, given some pattern of local operations and these causal constraints or some set of local operations that I'm allowed to do, what are the global operations that I can build up from doing those local actions? One thing that makes this subject really interesting is that there's some kind of interplay between the causal constraints that we have and the entanglement that we share as some initial resource. So in this setting, we could think of having not just system A and B here, but in general, some other quantum systems at these two vertices, which might be entangled. And then a classic result from a number of people here shows you that by having entanglement between the left and right here, you can actually, with this set of causal constraints, simulate anything that can happen in a network like this. Okay. So in this network, see the situation is a bit different. I can bring A and B together, do really any quantum operation on them locally that I would like, and bring the systems out again. Okay, so this result is saying that if I have entanglement here, I can also do any channel relating the inputs and the outputs. Yeah. So in this talk, what I'm concerned with is a more general setting where we have just a general causal network like this. So these would be some examples. So here I have 3 inputs and 3 outputs, and they can all meet. Here I have 3 inputs and 3 outputs, and certain pairs of them can meet and then get out to the outputs, and so on. I can think, many such situations like this. And then we want to ask the same kind of questions. Given a network like this and some computation that I want to do on the network, can I do it? With what probability can I do it? And how does having entanglement among the inputs help? and in particular, what pattern of entanglement, meaning which pairs of vertices need to share entanglement, and how much of that entanglement do I need to implement some given computation. Okay. So I think for this audience, I don't have to justify why we might study this too much, but just to mention a few things. So these sort of causal networks come up naturally in the context of position-based cryptography, which people have thought about a lot here. In that context, the network that's usually studied is the simple 2-to-2 one that I was describing. But these more complicated scenarios come up when you think about having many verifiers distributed in space-time. These things also come up in the context of, or just the general context of understanding how kind of quantum information theory and relativity sort of fit together, how the constraints from those two theories combine to restrict information processing. And then a connection that I'll talk a little bit about today is that these networks also come up in understanding subject in quantum gravity, which is AdS CFT, and sort of the relationship between features of space-time and patterns of entanglement in that kind of setting. Okay. You can also speculate, there's, people draw similar pictures when they're thinking about things like network coding and the quantum internet. You could wonder if these are also relevant to that setting, but I won't comment. Okay. So I just want to discuss in a little bit more detail how these networks come up in the kind of situation I'm going to be talking about. In particular, this question of understanding how information processing works in a space-time context, and then mention one general result that we have about these networks so far. So usually in information theory, if I want to tell you some information processing task that you need to do, I might specify for you the inputs I'm going to give you, and then the outputs that I want back, or maybe some condition on the outputs that I want back. In space-time, if I'm thinking about space-time, then a simple point is just that kind of description doesn't tell you, is not a complete description of your information processing task. So instead of just telling you the inputs and outputs, I need to tell you where in space-time those inputs start out and where in space-time those outputs need to end up. Okay, so instead of saying something like this, I'm going to instead draw some kind of picture like this one, where in this picture, time goes upwards, space goes left to right. And then I'm saying at this point in space-time C0, I'm going to give you quantum system X. At this point in space-time C1, I'm going to give you quantum system Y. And then at R0 and R1, you need to return X and Y. And then I also need to specify for you whatever transformation is supposed to relate the inputs and outputs.
So sorry, when you say that you give quantum system X and quantum system Y, they can be a joint state, right? And you give a register to one part and another part to another register, so no separated state. Yeah, so
they could be in a product state, or they could be in an entangled state. I'm just saying.
So
there's some degrees of freedom with X. Yeah. Any other questions so far? Okay. So yeah, this is the kind of setting I'm going to think about, and then these causal networks capture some interesting aspects of these settings. So this is where they're going to come up for us. So here I've drawn one of these space-time pictures. We have two inputs, C0, C1, two outputs, R0 and R1. I've drawn the light cones, the future light cones of C0, of the C's, and the past light cones of the R's. So this is just saying that if I start with some information at C0, then it can travel, into this region between the two lines coming off of there, but not over here, because that's going faster than the speed of light. And the set of light cones here defines some interesting structure that relates these points. And the statement I want to make is that this kind of a network captures that structure. So in particular, this network here is capturing the fact that it's possible to send information from C0 into this little diamond in the middle, and from C1 into this little diamond, and then out from that diamond again to R0 and R1. So having that kind of a causal feature can help you perform some information processing task, and this network captures that fact. Okay.
At any point of time, this middle nodes will be intersection of where both the both information could be in the same space at some point of time. Like the center node in the red directed graph. Yeah.
Yeah.
So is it like?
So this is not. So it's sort of confusing. This is a picture in space-time. Time goes up. This is just a graph. So there's no, it's capturing something about the space-time, but yeah. So I sort of, played a trick here in that the label C0 here refers to a point in space-time. The label C0 here refers to a vertex in a graph. So you shouldn't necessarily think of this point as living somewhere in the space-time or ask where it is, but it does represent its analog in the space-time picture is this diamond. Okay, so another example of relating these networks and the space-time picture is this one. So now it's a little bit more complicated. Time is still going upwards, but I have two spatial directions, y and x. One goes into the page and one goes across the page. Here we have that C0 can send a signal to R0 and C1 can send a signal to R0 and R1 and so on. These causal connections I've drawn with red arrows. I've represented those causal connections in the network like this. So C0 communicates to R0 and C0 to R1 and so on. But now here in the space-time picture, there's no place in the middle where everything can meet up and get out again. And so correspondingly in the graph, there's no vertex in the middle here.
Is this inherent to 2D? Like, could you get such a diagram from a 1D?
You can't get it in one. Yes, in the cryptographic setting, people draw these 1D pictures, and they're trying to think about, like, I guess there's some sort of imposed restriction that maybe someone can or can't do operations like in some spatial region in the middle. And so this picture the comment is just that this picture comes up in 1D if you're willing to sort of put in by hand restrictions on where you're allowed to do operations. You can sort of kill this by hand. But
is there like a new set of restrictions that appears in 2D? Maybe not for forward nodes, but for or do you care? Or I imagine that space does affect your.
yeah, I think how many dimensions you're in, what kind of geometry you're in, affects what kind of networks you can realize. We're going to see that. Yeah, we're going to go to some other kind of space-time and realize a certain class of networks there. Yeah, but I don't totally understand, like, given a space-time, which networks you can realize. It's probably hard problem. Yeah.
Maybe could you also like somehow limit the amount of stuff that, like, here for instance you have this middle node and it kind of goes with this diamond. The diamond has like some finite size or whatever.
Yeah.
Do you sometimes limit this, or is it?
So if you are thinking about, so in this talk, I'm not going to, but it is an interesting question. So, in particular, well, okay, it becomes a little bit exotic sounding, but if I was thinking about gravitational physics, then that imposes some constraint on how much stuff I can put inside the little box in the middle. And so you could wonder, here I'm kind of thinking about some fixed space-time. I'm not worrying about gravity right now. Correspondingly, the network that captures this situation, I'm letting like unbounded numbers of degrees of freedom flow on these edges, but you could try and think of some networks with constrained flows that maybe capture more of the physics of the space-time situation. Okay, cool. Yeah, so that's that's where these networks are going to come from in our setting, is they're going to fall out of these kind of space-time situations. I want to state one general result that we know about information processing in these networks. So this is maybe written down most explicitly by this paper by Kafir, who visited here a while ago recently. And basically the statement is that it's a little bit hard to parse, but it's simpler to just talk about the examples. The statement is that if I have some network like this, it has some input vertices and some output vertices, and some intermediate vertices, then if I replace that network with the one that comes from just directly drawing connections between inputs and outputs. So here, this point can signal this point via this intermediate vertex. And so I just add directly this edge here. Similarly, I can go from here to the middle to the right-hand side. So I'm going to add this edge here. If I just do that and cut out all the intermediate vertices in that way, then there's some initial resource state, some big entangled state that I can hold among the input points that lets this stripped down network simulate the original one. Okay. So this is the classic example from this paper I mentioned earlier from here. Here's another one where I've cut out these two vertices and replaced them with direct edges, and statements again, whatever I could do here, I could do here if I have some entangled state. There's many questions though about this entangled state. How big of a state do I need? Given a computation, how big of a state do I need? Another is just, do I need to say have direct EPR pairs shared between each vertex, or does it suffice to have some state that's entangled in some more interesting multipartite way? These are all things that we know very little about. And those are the kind of questions that I'm going to try and say something about using this quantum gravity perspective. Yeah.
Maybe a silly question. So I just want to check if I'm understanding it right. So you're saying here in this graph that you've drawn, so we are allowed to make some global unitary operation when the information reaches that diamond?
So any systems that are like all brought to one vertex can be acted on all together.
Yes, correct.
Yeah.
So that can be now replaced by some initial entanglement and local operations.
Yeah.
Oh, nice. Okay.
Yeah.
Okay.
So this was proven, and the language people would have used, like Harry would have used, or Christian, would be that position verification is insecure. So this relates to this position verification scenario.
Does entanglement dimension come here? How much resources are you actually want to subsume to get rid of all of them?
Yeah, so we know very little. We have, for certain unitaries, we have linear. So for certain unitaries, I could do like on this graph, we have linear lower bounds on the entanglement shared between the left and the right. So if I have a computation on n qubits, I know that I'm like n EPR pairs worth of entangled system. Upper bounds, we just know that for any unitary, you can get away with having an exponential size resource system. And then the situation, well, this one isn't too bad, but if I go to like more input points and more complicated graphs, then the best upper bounds use like some amount of entanglement that like gains more exponentials, the more complicated of a graph I have. So you can find graphs on like 3 inputs where I need 2 to the n EPR pairs, 4 inputs with 2 to the 2. So some horrendous blow up like that.
Better lower bounds?
No. So there's many open questions here that people are worried. Okay. Yeah, so in this talk, I'm not going to directly address that of like how big of a system do I need. I'm going to be more interested in, do I need like entanglement between each vertex directly, or can I have some multipartite state? Okay, so as I mentioned at the beginning, the perspective that we're going to take on this is going to fall out of this construction in quantum gravity called AdS CFT. You only need to know very little about AdS CFT, so I just want to describe that in basically one slide. So AdS CFT is this very interesting thing that it's a statement of equivalence of two apparently very different physical theories. So on one side of the equivalence, we have a theory of quantum gravity that lives in a special kind of space-time called an asymptotically AdS space. Okay, and that's going to be this cylinder picture that I'm going to draw a number of times. On the other side of the equivalence, we have a special kind of field theory called the conformal field theory that lives at the boundary of that AdS space. Okay, so the AdS space is the cylinder. Its boundary would be like a tube. I've sliced open the tube, I've laid it out on the page, and that's the rectangle that I'm drawing. Okay, and then the sides of the rectangle are identified, of course. Okay, some language. I'm going to refer to the quantum gravity side of this duality as the bulk and the CFT side as the boundary. And these things are supposed to be equivalent in a very strong sense, in that really anything I want to know about the bulk, there's some calculation I can do in CFT language to find out the answer, and vice versa. Yeah. Okay. 2 points to make about this. The first is that the quantum gravity side has a dynamical theory of gravity living in there. So there's a regime in which the bulk is described by like classical Einstein's equations with some quantum fields living on top of that space-time background. Okay, so in this bulk theory, there's all the gravitational physics we know and love, like planets orbiting around stars and gravity waves propagating and black holes forming and all this stuff. And the cool thing about AdS CFT is that all of that physics is in some obscured way written into this conformal field theory. Okay, so that black hole formation, that's some process happening in the CFT. Okay. One point to make about that is that one thing that means is that the geometry of the bulk, which is some dynamical thing, is fixed by the state of the CFT. Okay, so whether or not I have a black hole, like some geometric fact about the bulk, is fixed by the state in the Hilbert space that I happen to find myself in the CFT. There's like a CFT state that is a black hole state in the Hilbert space, and there's a state that's pure AdS or some geometric object in the bulk with no. Any questions about this? This is the most unfamiliar thing. So. Okay. We're going to take a sort of quantum information theorist's perspective on AdS CFT. It's a very operational perspective. What we're going to say is basically all these two theories are equivalent. Therefore, all of the operational tasks I can think about doing in the quantum gravity side are going to, in some sense, match up with all the tasks that I can do in the boundary theory. A little bit more specifically, we're going to think about these quantum tasks that happen in spacetime with points given at, or inputs given at different spacetime locations. So here's a bulk picture. We have some quantum systems coming in at point C0 here, some other quantum systems coming in at C1, and then I have to get some stuff out at R0 and R1 and R2. Okay. Then there'd be some particular relationship between the inputs and outputs that I want. I can think about that task, think about its probability of success. And then the idea is that because the CFT captures all the bulk physics, there should be some corresponding task in the CFT, which has the same success probability or related success probability, I should say. Okay. The way that you do that is sort of obvious. So here I've chosen the inputs. These in this picture, a point here is a point at infinity. So it's like infinitely far off. So when I say an input here, you should think of an input that comes in from infinity from a particular direction. Okay. points at infinity from the bulk perspective are identified with points in this boundary manifold. So that, this point here gets identified with this point here. Okay. And then once I've identified the points across the bulk and boundary pictures, I can identify what I mean by the same task in two pictures.
So it's an infinite element?
Yeah, sorry. So the picture is compact, but if I took a ruler and I measured the distance from the middle to the outside, that would actually be infinite.
But not on the torus. The torus is actually
This thing?
Yeah.
Yeah, the length around here is actually some finite number. It's, yeah, a strange thing. Yeah, okay. The way these two tasks are going to be related is that the success probability of the task in the bulk picture will lower bound the success probability of the task in the boundary picture. I've been saying these theories are equivalent, so it's a little bit mysterious why I would talk about an inequality here. That has to do with the fact that we're going to focus on a regime where the bulk is described by like classical gravity plus quantum field theory. I don't want to talk about string theory in the bulk. And that means that the physics in the bulk that I'm thinking about is some subset of sort of the physics in the CFT, which would in particular include all of the crazy stringy physics happening in the bulk. Okay, good. Okay, yeah, so now I want to get to this connection between this AdS CFT thing and these causal networks and start discussing what it teaches us about causal networks. So what we're going to do is we're going to take this kind of perspective on AdS CFT and pick one of these tasks. Let's pick a simple one with 2 inputs and 2 outputs. And what we'll observe is that that choice defines for me 2 networks. Okay, one network that corresponds to the bulk geometry, that captures the bulk geometry like I was describing in this earlier slide, and a different network which captures the boundary geometry. Okay. In general, those networks will be different. Okay. But the statement I made before relates computation in the 2 networks. So what is going to happen, or what this does for us, is this duality from quantum gravity relating these 2 theories induces some connection between pairs of causal networks. Okay. And in our general program of wanting to understand computation of these networks, that's going to be some useful tool where I get to sort of, instead of thinking about one network that might be hard to understand, relate it by this duality to some other one. Good. So in particular, if we're going to call gamma the network that's realized in the bulk geometry and gamma hat the network that's realized in the boundary geometry. And then what this inequality of success probabilities tells me is that anything I can do in the bulk network, I can do in the boundary network when it's equipped with whatever entanglement happens to be in the CFT. Okay. And so I'm going to schematically represent that relationship with this inequality because it's saying that this network plus that entanglement is more powerful than this other network.
What was determining the direction of the inequality in the success probability statement?
Yeah, so that was coming from the fact that I was restricting to semi-classical physics in the bulk.
But the boundary that corresponds to infinite n, so that's.
Yeah, I mean, okay, so we're going to think about fixing n, fixing some large n, sort of using. You happen to know AdS CFT, so I'm using some AdS CFT language. And then the point is that, for some fixed n, I can think about some procedure that I could carry out in the bulk that's going to complete the task with some success probability. And then the CFT has to have a description, it describes that physics, so it has some process in it that corresponds to that bulk process. And so that's this inequality. Any protocol in the bulk gives me a protocol in the boundary, and so the boundary success probability is at least as big as the bulk one. But the reverse doesn't work because if I have some general process in the CFT that could correspond to some very non-geometrical thing in the bulk, some stringy thing, I don't want to think about that. In particular, I don't want to think about that, and so that ends up giving me this inequality. So now our goal, since we want to understand these networks, should be to sort of pin down this relationship a bit better. So we could ask questions like, well, what kind of networks are realized in the bulk? What kind of networks does that correspond to in the boundary? And what entanglement does that come with in the CFT? Good. So part of the answer to that question comes from this, this general theorem that me and my collaborators proved, called the end-to-end connected wedge theorem. So I just want to step through some definitions that you need to understand that theorem. And then when it comes all together, you'll see what this is telling us about entanglement in these networks. So the first definition is, or sorry, I should first of all say that we're going to pick n input points and n output points in the boundary of one of these AdS spacetimes. The pictures I was drawing had 2 spatial directions and 1 time direction. Everything I'm going to say is restricted to that number of dimensions. In higher dimensions, we're still confused about what happens, but we can already learn things, interesting things here. Okay, so we're going to pick those points, and then we're going to make our first definition, which is of what's called the input region. That is all of the points that I can reach causally from C sub I. Okay, so V sub I is the future of C sub I, intersected with the past of R1 and R2 and R3 all the way to Rn. So the picture would look like this, where I have this light cone coming off of Ci, and then the past of R1 is like this thing. And so that restricts me to be in here. And then the past of R2 is like this thing that didn't restrict me anymore at all, actually. And then the past of Rn, comes down like this. And so I end up restricted to this little dot. Okay. The next definition is going to capture some aspects of the causal network in the bulk. Okay, so I have this bulk causal network gamma. And then I need to restrict myself to sort of some of the relevant information about that thing. So this is some new graph called gamma 2 to all. And the way that it's defined is given a causal network with n inputs and n outputs, I'm going to, sorry, this label missing, 1. I'm going to define a graph which has a vertex for each number 1 through n. And then in that graph, I'm going to add an edge between I and j. Whenever points Ci and Cj can get together and meet, and then get out to all of the output points. Okay, so here C1 and C2 can get to here, and then that point is in the past of R1 and R2 and R3. So I've put this edge here, connecting 1 and 2. And then similarly, 2 and 3 can meet and get to here, and so I've put this edge here between 2 and 3. And this is going to turn out to capture the right data about the bulk network that I need to keep track of. Okay. Similarly, I will define the same object, but for the boundary network. Okay. And I'm going to call that gamma hat 2 to all, because the boundary network was gamma hat. And then with that, I can state the theorem, which says that if in the bulk, the causal network is such that gamma 2 to all is a connected graph. It doesn't have to be complete, just connected in like a graph theory sense. And at the same time, the boundary network, gamma hat, is empty. Then this mutual information is big in some appropriate sense. So I've written order 1 over G Newton here. You can ignore that and read that just as big. Okay. The mutual informations that are big are sort of the bipartitions of all the V's. Okay, so there's V1 through Vn. Split that as a set into any 2 groupings. Okay, the mutual information across those groupings is what is big. It does not say, on the other hand, that like the mutual information between, say, V1 and V2 specifically, that can be small. Okay, good. So this is some theorem that's capturing for us where we have entanglement in the CFT, and hence what kind of entanglement the boundary network is equipped with. Let me show you that in some examples. So here's the first example I gave, where I have 2 input points and 2 output points. I've drawn them, or I've chosen them in this case in such a way that the 2 inputs can meet and get out to the 2 outputs. that means the 2-to-all causal graph here is this one. It has 2 vertices and 1 edge between them, so it's connected. At the same time, in the boundary geometry, what you can see is that that graph is now disconnected. So in particular, I could meet up between 1 and 2 like this, say, and now I could get to R1, but not to R2. Okay, so I don't have that 2-to-all connection. This graph is empty. Okay, so this is a situation covered by the theorem. Then what the theorem says is that the mutual information between these 2 regions associated with the inputs, so some blob down here and some blob down here, will be big. The theorem handles more cases, so here's a more complicated looking case with 3 inputs. Now I have a vertex or a place where everything can meet right in the middle. That means that the 2-to-all causal graph will be actually complete in this case, because 1 and 3 can meet and get to everything, and 1 and 2 can meet and get to everything, and so on. So that's what I have in the bulk. And then in the boundary, for this situation, I'll again have an empty causal graph or a 2-to-all causal graph. And so then what the theorem tells me is that all of these mutual informations are big. So 1 with 2 and 3 and the cyclic permutations. But you can also check that the mutual informations sort of pairwise between these things are very small. So that's the statement that we're going to use to understand, in this relationship between bulk and boundary networks, what entanglement we have, or what the boundary entanglement, what the boundary network, what kind of entanglement the boundary network has, and uses to simulate the bulk one. An interesting fact is that the proof of this theorem has almost nothing to do with quantum information theory. So the statement that I'm making is that these 2 networks can simulate each other, but the way that you arrive at this proof is actually by using tools in general relativity. And the connection there that relates these, lets general relativity tell you something about quantum information is this now quite famous formula called the Ryo-Takaaki formula. So what this says is that if I'm in the CFT and I would like to calculate the entropy associated with some subregion of my CFT, say this region R here, then the way that I do that is I look at the minimal area surfaces that enclose R, say this blue one. I take the area of that surface, I divide it by 4G Newton, and that tells me the entropy here. Okay. One thing that means that we make use of is that if, say you have 2 regions now, R1 and R2, and I want to look at their mutual information. Well, the mutual information is some linear combination of entropies. So this mutual information being large has some corresponds to some fact about minimal surfaces. And in particular, what it means is that this mutual information being big is if and only if the minimal surface enclosing the union of R1 and R2 sort of allows for this connected region between them, as opposed to this disconnected situation like this. So there's some geometrical signature because of this formula for the mutual information being big or small. Okay. And then,
somehow what's the one slide? Is it somehow some intuition that you can shrink away like the area if they're connected, and you cannot do this? Like somehow area of gamma should be order of G Newton, right, in the right picture, and it should be order 1 in the left picture. Is there some intuitive way of seeing this, or?
So remember that the mutual information is the entropy of R1 plus the entropy of R2 minus the entropy of R1, R2. So the question is, do these terms cancel or not cancel? And then if the entropy of R1 union R2 is calculated by a surface that connects R1 and R2, that means that the connected thing has less area than the sum of the 2 disconnected things. And then we are subtracting the area of the connected thing from the area of the 2 disconnected things. And then but anyways, the point is just that AdS CFT, in particular this formula, relates for you the geometry involved is this correlation. The way that the proof of this theorem then works is that you start with some geometrical conditions, in particular conditions on these networks in the bulk and the boundary. You use some tools from general relativity that I won't get into to relate that to the areas of minimal surfaces. I'm not describing the proof, but it should be plausible because this is a geometric object. This is a geometric object. General relativity relates those two aspects of geometry. And so there should in principle be some proof there, and indeed there is. Then you use this Ryu-Takaaki formula to relate that pattern of, or those conditions on minimal surfaces to the mutual information. And what you've ended up with is, this statement about networks that I was describing earlier, where, it's now saying that the boundary network equipped with some pattern of entanglement specified this way simulates the bulk network. And then that's some statement about quantum information theory that we have to try and understand and interpret. Okay, good. So before I keep going, I want to. So far I've written this inequality between the bulk and the boundary. I've said the boundary network simulates the bulk given whatever entanglement that we have here. It actually turns out to go the other way too. So let me briefly say why. So now we have this inequality. I can be slightly more precise. Before I said whatever entanglement was in the CFT. Now I'm saying this bipartition entanglement, which is this thing specified by the theorem. But yeah, we can ask about the reverse. As I was commenting earlier, you don't get the reverse immediately from the kind of reasoning about bulk and boundary tasks that I was saying. But it turns out to be easy to get just because, as it happens, the bulk networks that we're discussing here are able to implement any quantum computation. And so, if they can do anything, they can in particular do whatever the boundary network can do. And then that gives you the other inequality. And thus, these things are equivalent in computations that they do. Okay, so why can they do anything? Well, the condition we had in the bulk network was that this gamma 2 to all, this 2 to all causal graph was connected. And it's fairly easy to show actually that suffices for the network to be able to do any computation. So I'll just show that in an example. Here's a network with 3 inputs and 3 outputs. I have inputs A, B, and C down here. We see that the 2 to all causal graph is connected because these guys can meet and get to everything, and then these guys can meet and get to everything. The way that you do an arbitrary computation on this is you just send A, B, and C basically wherever. So let's in particular take A and B to here, and then C to here. And then from this intermediate point, we're going to generate some entanglement, distribute that among the 2 intermediate vertices, and then think about doing this computation just in the second level. Okay, so now we have A, B at this point and C over here, and a bunch of entanglement between them. And then we know basically on general grounds from this theorem I mentioned earlier from Kafir that you can do any computation here.
Maybe it's obvious from what you said already, but this resource that you have that for any bipartition you have this bound on the mutual information. Does it matter what resource state it is, or is it sufficient to satisfy this condition?
So all that this tells you is that there exists one resource state with that pattern of mutual information that does suffice to complete the task.
But is there some easy counterexample that some resource state that has this mutual information would actually not suffice? Is it?
Yeah, I think just something like the mutual information doesn't see the difference between quantum and classical, so you could just have well, I just have just classically correlated strings which have this property,
right,
and then that won't suffice.
Yeah, sounds good.
Okay. Yeah, and then so this is the proof for this simple case, but it just follows pretty easily that this condition works generally, and you can always do arbitrary counts without that condition. Okay. So putting everything together, then what do we get? Well, the statement we found is, suppose I pick these points and I find network gamma in the bulk and gamma hat in the boundary. Then, right, and I suppose that this bulk thing has two to all connected. Then what we learn is that the boundary network gamma hat, equipped with this particular pattern of entanglement, suffices to do any quantum computation related to input values. This raises some natural questions. One is that sort of exactly the right pattern of entanglement that I need? I.e., is that entanglement also necessary, or is there something even weaker that I could have gotten away with? And then another is, can we show this consequence of AdS CFT just directly in quantum information theory? Good. Okay, so I'd like to discuss necessity a bit. So let me say that. Okay, so a comment or a subtlety about this story is that the networks that you find in the boundary are a little bit odd. So an example would be this one here in the top left. It has 2 inputs and 2 outputs, and this set of causal connections that I've been discussing. But additionally, it has this funny property that at the outputs, you also get some quantum systems, which I've represented with these gray vertices, that were not included at the input locations, but there's no additional input given here. So it's like I get A system here, B system here. I need to do some computation on A and B. There's no inputs given here and here, but there is some extra systems that sort of come into play. Okay. So the AdS CFT consequence applies directly to these boundary networks. But it's also, I think, natural to consider the sort of stripped down versions where I get rid of the gray things and I only consider inputs where I actually, or input vertices where I actually get inputs. And
Is that like a random state or a fixed state?
it's a fixed state, independent of the inputs that are coming. Yeah. Okay. Yeah, so somehow we're also going to want to consider these. The story becomes a little bit more complicated. So for instance, in AdS CFT, we understand at this point, how to realize this in the boundary, but actually also how to realize this thing in the boundary, this one with the stripped off points. For n equals 3, like for more inputs, we don't yet understand in AdS CFT how to realize this thing with the gray vertices removed. And so we're going to still try and understand this. But when we understand this as opposed to this, the statements become more AdS CFT inspired conjectures as opposed to direct implications. The direct implications are for this network up here. Yeah.
This is an architecture that you are mostly using bipartite entanglement. Is that what? And kind of you've leftover stuff if you have too many parties.
It's basically like, I mean, it's already present in. So let's think about this situation, for instance. So here I said this causal situation of this space-time picture was represented by this network. But if you want to be careful, I mean, there's also in this past light cone of R0, there's also some systems that could come in like this that were separated from C0 and appear at R0 at the end. So this picture doesn't actually capture everything in the space-time. Formally, it also has these extra gray things, but we just normally don't think about them. And yeah.
But the graph.
So they come up similarly in the AdS CFT context. Like that
But
there's,
you need them in some point in the graph to do the same calculation.
it's not clear. So we we know that with them, you can do the computation. That's an implication. Well, one, an implication of AdS CFT, and two, something we can reproduce directly in quantum information theory. Without them, we have some evidence that you can complete any computation. We'll discuss that, but we haven't fully been able to do that at the quantum information level, and it's also not directly implied at the AdS level. Yeah.
Is it possible to give like some concrete example of a research state that will suffice for this, from maybe some kind of mirror tensor network construction, maybe for the CFT state?
Yeah, you can wonder about that, and you know, yeah, more broadly, that's in the vein of like, oh, the AdS CFT tells us we can do this thing. Can we use some aspects of AdS CFT to actually like import those over into quantum information theory and use them in some direct way? Yeah, in some discrete way. I'm going to discuss something, I mean, not quite what you suggested, but something in that spirit.
So so that's something you're considering?
Yeah, that's something we're working on. Yeah. Yeah.
So I have heard that it's believed that maybe QPV can be attacked with a linear amount of entanglement, and that idea comes from here, I think. Is because of these vertices not being clear to be necessary?
Yeah, so, okay. One comment is that in QPV, we usually think about this network. And there, okay, it's not published yet, but there's work showing that you can actually get AdS CFT to tell you about how much entanglement in this picture, like without the extra gray things. So there's really this sharp connection between what we usually discuss in QPV and AdS CFT. I wouldn't say that AdS CFT implies you can do everything linearly, but it does say that sort of whatever you think you can compute in the bulk of AdS. So there's many questions about that. Gravity is present. Fields might be a bit exotic in the bulk of AdS, might have supersymmetry. But whatever you can compute in that gravitational situation, you need to be able to compute, in this non-local computation scenario using however much entanglement AdS CFT has. I think, maybe we should discuss this later because it's a little aside from the main subject here, but I think there's some tension in what you would expect you can do in the presence of gravity and what we know how to do already in non-local computation, but there's no like sharp disagreements between those things at this point. Okay. We start 5 minutes later, 10 minutes later. Oh, sorry. Okay. Right. So let me mention necessity. Oh yeah, that's okay. So I was talking about necessity. So in these stripped down networks without the gray things, you can actually also show that this pattern of entanglement across the bipartitions is necessary. Okay, so yeah. Good. The way that works is kind of cute, I think. So there's a more general version of this, but let me discuss it again for this n=3 case. We want to show that, here we're going to show V1 and the union of V2 and V3 have to be entangled. The way that this works is we're going to choose a task with just 2 inputs and 2 outputs, but we're going to place the inputs and outputs carefully. In particular, I'm going to put an input here and an input here, and then an output here and an output here. And I've done that because I wanted to offset it from the kind of causal connections that I had, right? So if I had outputs here and here, I wouldn't be able to get anything because obviously I can just do the computation by acting locally in the middle. But by shifting it like that, it's going to force us to use the entanglement. Okay, so I do that. Then we note, okay, well, this output is just unused. And so sending things there is not going to increase my success probability. And so that means this network with that output erased, the success probability there will bound the original one from above. Next, I'm going to note that if I, here I sort of get to act separately on V2 and V3. It will only help if I let you act on V2 and V3 together. Okay, so I'm going to group those vertices together and make a new graph. And again, that's going to increase the probability. Then this funny looking network we can simplify. In particular, it never helps to send information like into one of these 3-point vertices, do a computation there and send it out here. I could have just instead directly sent things to the output and done whatever computation I did at the 3-point vertex near the output point. Okay, so that lets me simplify these 3-point things down basically by pulling, you know, the intermediate vertex up to its output point or down to its input point. And that relates me to this fourth graph, which is this one. And again, I have this inequality. This graph, fortunately, is just this standard 2-to-2 scenario that has been studied in the context of position verification, and for which we know there exist unitaries where I need some mutual information between, you know, the resource system on the left and the resource system on the right. But now the trick, right, is that, so here I know that the left and right systems have to be entangled, but now the left and right systems consist of V1 and then the union of V2, V3. And so I end up with a lower bound on this thing. Yeah, so that's where necessity comes from. It's from this grouping of vertices that I end up with this bipartition. Okay, cool. I will just say a little bit about it because running out of time. But so we've also been thinking about these stripped down networks. Okay, let me first of all remind you that AdS CFT is just telling you that in this network with the extra vertices, you should be able to do any computation while having only this bipartition kind of entanglement. So 1 is entangled with the union of 2 and 3. That's really easy to show. You can actually use a generalization of something Florian pointed out to Kafir to do this. It's maybe not totally obvious, but yeah, it's not super hard. Yeah, so that's implied by AdS CFT, and we understand how to do it on the QI side, so that case is sort of resolved. But then there's the harder question: is if this remains true when I remove these sort of inputless extra vertices. For n equals 2, for this case, we know that that's the case. We know that that holds, so we can do any computation in this thing with bipartition entanglement, which is just both the inputs are entangled. You can get that either from AdS CFT in this extra geometric construction that I described, or just from these original QI constructions in QPP literature. But yeah, there's an open question here for a network like this, if you can do any unitary with that kind of correlation or not. Right. So I will point out or outline a way that you can do any Clifford. Any Clifford relating inputs and outputs you can do in this network with that kind of entanglement. And you can, for people who know what it is, you can also do an arbitrary F routing task, again, with the same kind of entanglement. So that's some evidence this will be true for all computations, but that's not clear yet. The way that this works, and coming back to a question we had earlier, is we're going to think about what's happening in AdS CFT and sort of the structures that it's using. And it's going to turn out it's using a sort of interesting error correcting structure. And by porting over that kind of error correcting structure into our protocols, we'll be able to understand how to do all of these Clifford unitaries. So yeah, a fact about AdS CFT is that if I think about one of these boundary subregions, let's say R, and I think about the minimal surface enclosing it, that minimal surface plays 2 roles in that its area defines the entropy of that region or calculates the entropy for you. But it also delineates or is the boundary of the portion of the bulk that subregion R sort of knows about. So if I have some qubit sitting in the bulk, let's call it A, if it's inside of that region bounded by the surface, then it's reconstructible in R. Okay. So there's this error correcting structure because if I move R around the boundary, many different choices of R would all be able to recover A. Okay. Good. So yeah, I'll just wrap up. So basically, you can think about in the bulk picture, how this computation happens is these systems fall into the bulk. And falling into the bulk is basically getting recorded into one of these error correcting codes. And the way that you implement an E-Clifford on one of these networks is analogous. So you start with the inputs here. You exploit the pattern of entanglement that you have, in particular this bipartition entanglement, to get this, this state recorded into an error correcting code distributed across the intermediate vertices. You use some transversality properties in the code that you put it into to implement the computation. And then you use the remaining causal structures, these remaining set of edges, to extract systems out of portions, like subsets of degrees of freedom code. Okay, so that's all I'll say about that. Yeah, and I'll just wrap up and make this